Welcome to Mrs. Mahoney's podcast. This is our first one of our Unit 9, and we are on page 2, so starting the unit off. We're going to be covering gas laws. Now, you probably want to reference this, put this down. This is going to be chapters 13. It's kind of the theory, and 14 is going to be the problems in our book. So if you need to go back and reread some of the things, this is where you can find it. Chapters 13, the beginning of chapters 13, and then pretty much all of chapters 14. So let's kind of look at this kinetic molecular theory. Okay, now we're going to abbreviate this. A lot of times you're going to see this as the KMT, Kinetic Molecular Theory. Kinetic movement. So what are we talking about is the movement of particles, more specifically the movement of gases. Well, there's 5 kind of postulates that we're looking at for the kinetic molecular theory. First one, all gases are composed of extremely small particles, and here's a big key difference. Those small particles, because everything is made of very small particles, atoms. Difference, there's a very, very large distance between those particles. That is the definition. That's what makes it a gas. Because we talked about with those solids, they're really, really compacted together. Solids, very compacted together. Liquids, still small particles, a little bit more space. That's how come you can get them to flow. Gases, they are all over the place. They have large distance, more than I could even draw, but I think you get the idea. Okay, there's an elastic, all gases would have elastic collision. That means no energy is lost during a collision. That would be like if you take 2 ping pong balls and we were able to throw them directly at each other and they would totally bounce off each other, versus if you take 2 pieces of Play-Doh and throw them at each other and they would tend to stick. The Play-Doh would be inelastic. The ping pong balls would be elastic, so there's no energy lost. There would just be a transfer of that energy. The third one, particles are in constant random motion. And you can see that when we look at the dry ice, or you can get a gas, you can smell. The reason that's why we can smell things, because those particles are a gas and they're constantly moving, and that's how you can smell perfume across the room. Okay, so our fourth thing we're looking at, and again, these are all describing the perfect or ideal gas. There's no attraction between any of the gas molecules, which again leads up to this number 2. That's why there's all the collisions are elastic. There's no attraction between the molecules, so they just kind of like bump into each other and keep on moving. So there's no strong magnets, nothing attracting them. That's why they're in that constant random motion. These all kind of relate to each other. And then our last one, the average kinetic energy depends on temperature. Now remember, kinetic energy, kinetic is movement. And it depends on the temperature. So the higher the temperature, what does that mean about the movement? The faster the movement. So that's why when do we get gases? We get gases at higher temperature because the particles are moving faster, and they're moving fast enough to break this attraction that they had in the liquids. And that's why you don't get this attraction, because the temperature is so high, the particles are moving so fast, they don't get this chance to have the attraction between the molecules. So these are all describing that perfect, that ideal gas. This is how it would act. Well, let's look at some of the properties of gases. Now, most of these you should know what they are, and we'll add just a couple little words or definitions. If you do not know, especially, kind of add to it. Expansion, if something is expanding, what does that do? Well, this is why they fill any container. So they can expand, get bigger, to fill any container, and that's one of the definitions of a gas, that it's not a definite volume. It's going to fill any of the containers it is. If it's in a small test tube, I open it up into the room, it would expand over time to fill the room. Okay, fluidity. What does this mean? Gases can flow. And again, I'm going to reference that dry ice. Remember when we had the dry ice, when I was doing the day of the demos, and you could see the gas, the carbon dioxide flowing. You can almost see if you pour it out of a beaker, gases can flow. Low density. Okay, density is mass over volume. So what does that mean? Gases have a low mass that cover an extremely large volume of space. Helps if I can spell. A large volume of space. This is how you get a low or a small density, low mass covering that large volume. Compressibility. Compressibility is kind of the opposite of expansion. Expansion is going to fill a container. Compressibility means, common words, you can squeeze it. Squeeze to make smaller. So that is how you take a balloon in your hand, and can you compress it and make that balloon smaller? Yes, because you are compressing, squeezing that balloon, squeezing the gases inside that balloon. Okay, diffusion is pretty much when it moves from a higher concentration to a lower concentration. It's when they're going to kind of spread out. This is why, let's see, if a skunk came into the room and we all ran and somebody thought it'd be really fun to lock us in, and even if it ran to the far corner, if we ran to the opposite corner, and if somebody decided to go and get it, decided, Mason, thank you, you decided to go get it, and it squirted, well, you know what happens? We would still not be safe, because even if it squirted on this side of my room and we're all hiding way over here, all that gas is going to diffuse and we would smell it. This is why when somebody's spraying cologne or perfume, you can smell it even though we weren't standing exactly by them. It's a gas. It's going to diffuse and spread out. Okay, it's a little different than effusion. Effusion is when a gas escapes from a small hole, or they get through a small opening. From a small opening. This is why if you get a tire puncture, just a little nail, your tire will still go flat, because if we have some kind of a balloon even, there's a hole right there, all the gas can escape out of that hole. Now with effusion, the faster particles are the smallest. It's all kind of about their mass and their size. Fastest particles are the smallest. That's why if I have a helium balloon and you try to put it just in a normal latex balloon, in the morning, that helium balloon, all the helium particles are going to be gone. Look at helium. It's a small particle. Look at its molar mass compared to what air normally is. We know air is normally nitrogen, oxygen. And so these are, 28, molar mass of 28. This is molar mass of 32 compared to helium that has a molar mass of 4. So that's why the helium particles will escape through a latex balloon. They're only good for about a night. Put them in a mylar balloon, the shiny ones which have smaller openings, that's why they're going to last longer, because it's all about the size of the openings. So the helium is going to escape faster out of the latex balloons because it's a smaller particle and it's going to fit through the holes, the openings in the latex balloon. So effusion is a pinhole, gas escaping through a pinhole. Diffusion is just the gas moving from a higher concentration to a smaller concentration. All of this happens because those particles are in constant random motion. Okay, so an ideal gas then is that perfect gas that follows all of those kinetic molecular theory assumptions under all conditions. So that's our perfect gas. Well, not all gases will do that. In fact, they really don't do that. So the real gas are the ones that fail to follow it, but we can get them to become pretty close to ideal. And actually the gases that come the closest to ideal are your noble gases, because again, no attraction between molecules. Also your diatomics come very close to ideals. And again, these are because they are nonpolar covalent. No attraction between the molecules. And that attraction between the molecules is when they start becoming more real. That's going to slow them down. That's going to make them deviate from some of those rules. So what are these conditions? Well, I say it's kind of like you guys, and think of you as the perfect student. When are you the most ideal student? For most of you, it's probably in the summertime because before you get started your junior year and your summer, you're like, okay, next year, this year, I am going to do all my homework. I am going to study. I am going to work hard. I am going to ace it. I am going to do everything I need to do. So in your mind, you are this ideal student. You know what you're going to do. Well, think about the summertime. What is it? Hot, high temperatures, and you have no pressure because it is summer. You don't have to do the homework. You don't have that stress. Okay? Same thing with the gases. Low pressure, high temperatures. So low pressure, we're not squeezing the molecules together. High temperatures are moving very fast. So when we are this, what you have done is you have limit the attraction between the molecules, and that is going to again make them act more ideal. So when you can limit the attraction between the molecules, that is when you're going to see more, they follow the kinetic molecular theory more. Well, we're going to start looking at some specific ideas, specific variables, and these are the three that you need to know: pressure, volume, temperature. We're going to look at them mathematically, and you also need to be able to recognize them when I give you a scenario. If I change one and keep something constant, how's the other one going to be affected? Now, most of these you have had some kind of personal experience with. So this first one, let's look at this pressure. And if you've ever gone up in a plane and you decrease the pressure as you go up higher in the plane, and then what happens if you have any kind of bag of chips or anything that's not being pressurized, that bag of chips gets really, really big. So on these, as your pressure goes down, the volume will go up, or vice versa. As I squeeze something, take a balloon. Squeeze the balloon. You are increasing the pressure on that balloon. What does the volume do? The volume goes down. Okay, so what's this relationship look like? It's not a straight line. This is when we kind of get our parabola looks. It's an inverse relationship. All these things I'm writing, I would be adding them around the picture too. It's an inverse relationship. That's when one increases, the other decreases. Okay, this has a name. His law, this is known as Boyle's law. Boyle's law relates pressure and volume. Okay, let's look at our second relationship. We're looking at this time pressure. How does it compare with temperature? Well, if you have ever, I know none of you have ever done this, but if you're camping and you decide to throw an aerosol can into a campfire, well, what's happening? That temperature of that can is going up and up and up. Well, that can, what's inside, the pressure inside of that, those particles are moving, and pressure is how many times any particle hits the side of a wall. The more it hits the side of a wall, the higher the pressure. So as it starts going faster and faster, because the temperature is going up, your pressure is getting up to the point that that can cannot hold the temperature anymore, the pressure, and the can explodes. So what do we have? It's a direct relationship, because as that pressure goes up, the temperature goes up. Or again, vice versa, as the temperature goes down, the pressure goes down. This is a direct relationship. The direct relationship. This was named, again, they have some discussions, the Gay-Lussac's, looking at this, and it's again the pressure temperature. Again, name for the people who first identified the relationship and kind of put it all together. Okay, let's look at our last one. Volume and temperature. This is how a hot air balloon works. Because if I have a hot air balloon, what happens? They increase the temperature, and that makes that volume, there's Panda, so that makes, if I increase the temperature, that makes the volume is going to go up. So look at what happens. Density, again, mass over volume. So the mass of the air is going to stay the same, but the volume of the air increases, so that makes the density greatly decrease. You know, things with a smaller density are going to rise, so that's what makes the hot air go up, the hot air balloon go up. So also on this one with temperature and volume. Doesn't have to be that sharp of a line, but what do I want to know? That volume goes up, temperature goes up. As volume goes down, temperature goes down. So this again is a direct relationship. This is known as Charles' law. So you do need to be able to recognize the variables, and we'll kind of talk tomorrow. There's actually a little tool or a hint, and it's actually you're holding it in your hand with your pencil that you can kind of use to help learn the relationship or use it as a memory tool. But really think about things you know, and a lot of these, if you can think about things that actually kind of you've seen. I put the chips in my car. As the temperature of that bag of chips has been sealed goes up, the volume of air in that bag of chips goes up. Most of these you've seen, and tomorrow in the lab we're actually going to try to see all three these relationships a little bit more. I will see you tomorrow.